how the reader convinces
Accumulate.
A cup of tea, so
No.
which is not true because I know several who did.
It's a terrible thing to say, even if I thought it was true.
okay, the last lecture today is under the full responsibility of Pierre Duclos. And I don't know how to introduce it otherwise with all this list, on graph models of mesoscopic systems, waveguides, and nanostructures.
Thank you very much, Michael. So I would like to thank Pavel Exner, who took the responsibility to invite me to this conference. And because I am not at all an expert in graphs, in quantum graphs, but the topic I will discuss today has something to do with the part of the title of the conference, which, let's say, mesoscopic system, waveguides, and nanostructure. In fact, Michael, the title is On the Skeleton Method.
Sorry.
Now, about the title, the skeleton, we heard this word this morning in the second talk, I think. And method, it's not very exciting because if you go to a conference and try to teach a method to people, this is not very important. They prefer to have a result about topic and subject. So I will, in the first part, explain why we came to this method, and then I will speak about the method in the rest of the talk. Now, this method is mostly about whether quantum systems which interact through delta potentials, they are solvable or not. There is a common wisdom that if you speak to somebody and tell them, I'm doing a system with delta interaction, they say, yes, this is trivial, one can solve it, etc., etc. But in my opinion, the answer is no, except if you have many symmetries. But if you have not enough symmetries, you have no chance to solve the problem. Of course, if you take two particles, this is solvable, this is very well known. But if you take n particles, you have no chance in general to solve this problem. By n particle, I mean I let the masses and the charge and the position, of course, the position, the masses and the charge to be general. But we are going to put a lot of symmetries in order to be able to do something. Now, this method, I learned it from an old paper by Rosenthal in 71, who was trying to solve the helium-type atom interacting through delta potential. So you have the nuclei, which with infinite mass at position 0, with charge Z, and 2 electrons, which charge -1, with, and here the mass, they are equal, M1 equal M2. Now, if you look at the support of the delta functions of the potential in the plane x1, x2, you get this picture. As a general policy, I will take red color to indicate positive charge. Yes, Robert?
You're in one dimension, right?
Yes. This is one-dimensional delta interaction. Thank you very much. And black color to indicate negative charge. Now, in a paper by Exner and Ikinoza in 2001, they introduced the terminology quantum leaky wires to indicate such type of model. Namely, you have a delta interaction supported by a line in the plane. Here, this is not one line. There are several lines, and they are of star graph type because they all cross at the same point. So because of this analogy or this other point of view on this model, I feel allowed to speak at this conference. So what is the question? The question is, what was the question that Rosenthal was asking? What is the minimal charge on the nuclei you have to put in order that the system is bound? And here in this problem, in this quantum leaky wires problem, this is the same question. We ask what is the charge we have to put here so that, because you have something repulsive and something attractive here. So what is the charge you have to take in order to have at least one bound state? Now, in fact, this is like a graph, with the support of the potential, but of course you have tunneling between the support of this potential due to the fact that this is not a wire which is independent of the rest of the plan. Huh? So this is something we could eventually call leaky graphs. Now, in another paper, but I'm a bit ashamed because I don't remember the name of the three others, but the E is Exner. Pavel, I'm sorry about that, but Bulgakov, the first one, and two other one, could you pitch in? And Sadreev, yeah, thank you. They consider so-called quantum scissors. What is a quantum scissors? This is two waveguides which cross like a scissor. But these waveguides, they have directly boundary condition on their side, so they don't communicate except through the crossing. Here, I will put a delta function on these two black lines, but of course there will be tunneling between the two lines. And I have chosen this very simple model just to explain what is the method about. And because there is no point of starting with complicated system. And even I have tried to list what are the questions of these four people wanted to answer in this paper. And I have put them on the screen. But I will not answer to all of them. There will be only very partial answer because I only decided to work on this problem for this conference. Previously, I was working on other problems I will indicate at the end if I have time. So, existence of bound state, monotonicity with respect to the angle theta. But theta, in the paper of these four persons, they take this angle theta. In my case, I will take this angle theta for obscure reasons that I don't want to explain. And the theta 1, 2, because 1, 2 refer to these two vectors, will go from pi over 2 up to pi. This means that here the maximal angle will be pi over 4 and pi over 4. And we will add this guy goes to the straight line. Number of bound states intertwining between even and odd state because you have symmetries in this problem. Behavior of the splitting between odd and even bound states because they group by pairs. And critical theta when new bound states appear in the game. Now, I continue the list of problems. In fact, by the way, this is for this problem that I came to this method. This is a problem of three particles on the line, one positive and two negative. If you go to Jacobi coordinate, remove the center of mass, you arrive at an operator, remove the center of mass, you arrive at an operator of that type where you have the delta function supported on these three lines, repulsion and attraction. And now you have two angles in the problem. And the link between the masses and the angle is indicated here, but you have to forget about it. Now, another problem, which is supposed to mimic an exciton in presence of impurity in the carbon nanotube. This is a fixed positive charge and a negative and a hole and an electron, because as was explained this morning by Horia Kornean, one can modelize a carbon nanotube, an exciton on a carbon nanotube, first as two particles oppositely charged on the cylinder, and then go to the line and having delta interaction. So this is quantum leaky graphs associated to this problem, but probably I will not discuss this model today. This was something I presented in Prague in September, and now there are new results, but probably I will not have time to. And in order to have an example which is not star graph, I consider an H2 type molecule on the line. So you understand this is a x1 coordinate, x2 coordinate. This and this are, we are in the Born-Oppenheimer approximation. So this and this is the position of the nuclei, and here and here. And this is the repulsion between the electron. And this type of operator is meaningful in high magnetic field, and I will explain that in a moment. This is now the explanation why should we work on that type of model. Why is it interesting? Because this could look like just a game, but not really, because in fact one can prove mathematically, or one can prove, I'm sorry, that if you consider an atom with n electron in a magnetic field, homogeneous magnetic field, and if you let the field B goes to infinity, this operator is asymptotic to this delta model operator in the norm resolvent sense. So this means that if you want to study this operator for a large field, you could start with such naive model and do perturbation theory. Perturbating from B equal infinity to infinity to some value, I value of B. Of course, I have said asymptotic because both operators have no limit, but they are asymptotic. And as was explained by Horia Kornean this morning, if you look at exciton, trion, bi-exciton on carbon nanotube, you start by putting several particles on a cylinder, and then you let the radius of the cylinder goes to 0, and you can prove that this operator interacting through Coulomb potentials converge, not converge, but is asymptotic to this operator, which is again a delta model type of the type I have introduced at the beginning. So this is the motivation. Now, what are the things we would like to study? This is known that if you have systems which are one-dimensional, the binding is enhanced. So we want to study this property. When the magnetic field goes to infinity, then you have the appearance of new atoms and molecules, in particular at the surface of neutron stars. As Horia Kornean explained this morning, this exciton, this strong binded exciton on carbon nanotubes, they modify the optical response. This is important for example, sorting carbon nanotube. Problem of localization of exciton in carbon nanotube by impurities, and also bond state in quantum leaky graphs. Now, I will start to try to explain the method on this simple model that I call quantum leaky scissors. So again, this is, you have a two-dimensional particle in the plane. and which sees the potential supported by these two lines. And now A1, and A1 orthogonal means I rotate the unit vector by pi over 2, and the same for A2. And as I have said already, the angle θ12 will be between pi over 2 and pi. First question we have to cope with is the localization of the essential spectrum. This is obvious work. You have just to adapt the HVZ theorem because you don't have really two particles, because you don't have repulsion. But nevertheless, it works, and you get this essential spectrum, -1/2 infinity.
That's the essential spectrum of the effective one particle operator.
Of this operator.
There's a one particle operator.
Yes?
Yeah, there is 1/2 at Laplacian because.
Yes. You see, this is the square of a 2 now because of the
Okay.
2. Yes. This is one particle. This is why I cannot really say it is HVZ. If I would have a repulsion delta x1 minus x2, then I could apply HVZ. But you just adapt HVZ theorem. This is. Now, we are coming to this skeleton. So I introduce the operator which takes the trace of a function in sub F H1 into L2 of R. And I index this trace operator by the unit vector which directs the line on which I do the restriction. So this AI is a basis, if you want. And then I introduce the collection of the two trace operator on my 2 line. And there is a mistake here. This is 2, huh? Because I just copied the problem with 3 particles, and I forgot to put the 2 here. Now, of course, my operator can be rewritten like the free Hamiltonian plus this operator. And now doing Resolvent formula, or if you want Krein's formula, because in that case it could be called Krein's formula, you can compute the resolvent of H in terms of H, the resolvent of H0 time or minus this operator. Now, this operator is the one I am interested in. And there is a little lemma which is here, which says that if you take an energy which is below the essential spectrum, this energy, I call it minus k squared. This means that k, in my case, will always have to be greater than 1 over square root of 2. So is an eigenvalue of H if and only if the kernel of this operator is not reduced to 0. And if you do a scaling by removing this energy E, this is equivalent to looking at this question, whether this operator, where now the spectral parameter is here, whether this operator has a non-trivial kernel. And you have also a relation between eigenprojection, but I don't care about that today. Now, I will call skeleton this operator. And of course, I also call skeleton the one before the scaling that I indicated just 1 minute ago. This operator could also be considered an operator pencil, because I have some friends here who like this operator pencil, because the spectral parameter is put in a non-trivial way. So this is, in the terminology, the Russian terminology, this is operator pencil. But of course, you could also say this is just the Biermann-Schwinger kernel, up to some trivial transformation, because this is the Biermann-Schwinger kernel, and this is the operator I will consider, or this one. Now, if I compute explicitly this operator I call skeleton, this is, I will have a 2x2 matrix of integral operator acting on L2 of R. This, this is the integral operator we shall see in a minute that these operators, they are in fact multiplication operators, but this one, they are effectively true integral operators. There are some similarity in notation with respect to the previous talk, because Professor Kostrikin was writing S of k for the scattering matrix, but this has nothing to do. Now, this operator, which sandwich the free resolvent between this trace operator and the adjoint of the trace operator, we will discuss a bit, not a bit, we will discuss very much them during this talk, because in fact, this is the idea, or the ideology, that it could be worse to work on this operator instead of working on the Schrödinger equation. This is a message I would like to deliver tonight. So take two unit vectors and define TAB like that. This is an integral operator acting on L2 of R. They are sometimes called singular Green's operator by Putel-Monvel, by Gerd Grube, by this is at least 2% that I have heard speaking about that. You can compute explicitly the kernel. This is trivial. So when the unit vector is the same, this is just a multiplication operator by this function, 1 over square root of p squared plus 2. And if the two unit vectors are not parallel, then you get such integral operator, which is explicit. You immediately see that this operator depends only on the absolute value of theta, which is a bit normal if you think a little bit, because the free resolvent is invariant by rotation, by translation, so this is not important, the angle, etc., etc. But you can see it from analytical calculus. Now, because of that, I will rather call the T operator with the angle, and even sometimes with the index which indicates the unit vector which directs the support. Now, they are Hilbert-Schmidt. You can compute their Hilbert-Schmidt norm, and you find this expression. And you see that when theta goes to 0 or pi, it diverges, which is normal, because theta and pi correspond to multiplication operator, so it cannot be Hilbert-Schmidt. Now, you could also have a trivial bond in the operator norm, which is 1 over square root of 2. And this is an exercise to realize, first of all, in the case where the two vectors are parallel, this is a multiplication operator. And you know that the norm is just the soup of the function. So this is 1 over square root of 2. Now it is trivial to compute the norm of this one from this one by doing Cauchy-Schwarz. If you do Cauchy-Schwarz, that gives you immediately that the bond of this one is bounded by this one. Now, there are also symmetries. These operators, they commute with the parity operator. So we can decompose T theta in the positive and negative part, which will be important. Now, using this symmetry property, there is another symmetry property in the problem that I am looking at. On the skeleton, if I exchange the two restrictions of the function on the line, it commutes with the skeleton. So I have two symmetries, which have two sectors each of them. So I have 4 sectors. I decompose my skeleton in the 4 sectors, and that gives me this just you have to trust me. From the 2 by 2 matrix, I come up to 4 simple integral operators on the line, which is k minus t0. T0 means angle 0, t1, 2, angle between the two positive part, etc. the essential spectrum of this operator is like that. Why? Because we have seen that, not here, it was even before. There is a diagonal part which is a multiplication, and the off-diagonal part which is compact. So the essential spectrum is given by the diagonal part, but this is just a multiplication operator by an explicit function, so I compute the range, and this is trivial. Now, let's see. So this picture is wrong. Don't look at it. I will consider first the function which are odd with respect to the x2 axis. So let's come back. So there is a list here. Pi2 is a parity operator with respect to the x2 axis. So I consider these two. They are odd with respect to the x2 axis. So this one and this one. Suppose I know that the positive part of this T operator is positive. I mean, the plus part of this, or even part of this positive of this T operator is positive. And suppose, and I remember that I have to take k larger than 1 over square root of 2 because I know the essential spectrum, and I know that the k square has to be smaller than -1/2. So if I have these two conditions, of course, this operator is greater than k minus 1 over square root of 2, which is strictly positive. And remember that to find a bound state, I need a non-trivial kernel. So the kernel is reduced to 0. There is no bound state. Same reasoning here. Suppose I know that the odd part of a T operator is negative. By a similar reasoning, I arrive at there is no bound state. And now this directly should not be directed like that, should be directed like that. So this means that because I was more occupied in preparing pictures than thinking, so I'm sorry about that. So the parity with respect to the being odd with respect to the x2 axis means being directly here. So you take the picture, the half of the picture, for example, from the top, and this problem has no bound state for all angles between pi over 2 and pi. Now, since I have said that the even part of the T theta operator is positive, I have to prove it. So I write, I do first the exercise for the angle pi over 2. This is the kernel of the operator. The kernel is positive, but you know that if you have a matrix with positive entries, that does not tell you at all that the operator is positive. So, how would you prove that this operator is positive? This is not, I mean, at least for me, it took me time to find the solution, but this is a colleague who told me how to do it. Forget about the red color. Look only at the black color. Just rewrite this kernel with this Laplace transform. Now you see that this operator is just a rank 1 operator. So you have represented the operator as the integral of positive operator. So this means that the operator is positive. Now for the general theta, this is just now cooking. You, the positive, the plus part is just obtained by taking the kernel and changing q in minus q. So you have now you compute, right, as a series. And now you see that below we have an expression of the same type as here, except that I have this exponent, but I have to put this extra. And on the top, this is a product PQ. So this is again a rank 1 operator with vectors which are not positive, but which are not bounded, but this is not important. Of course, one has to prove that there is convergence, etc. But at least this is the way to prove that these operators they are positive. Here I have used this scaling, but not important. So the statement is that this T operator, the even part is always positive for all angles. And if you do the calculus for the odd part, you find that it has the sign of cosine theta. Namely, above pi over 2 it is negative, below pi over 2 it is positive. And in particular, the odd part of the T pi over 2 is just 0. Now, let's discuss a sector. So I don't remember exactly what means this index, but this is this skeleton we are going to study. So what now you see, this is negative. And what? I want this guy to have a non-empty kernel. So, okay, I factorize square root of k minus t0 on both sides, and I arrive with this operator. Now, if this operator would have a bond would be bounded below by -1, then I cannot invert. I can invert, so the kernel is reduced to 0. So I need to prove that this operator is bounded below by -1. So this is first a numerical exploration. So I go from pi over 2 up to pi, and I compute the spectrum of this operator. This is a green line for each angle. And you see that the lowest eigenvalue cross -1 exactly at 2 pi over 3. And, but this is numeric, so we would like to have a mathematical proof of this fact. So numerical result says that for all angles between pi over 2 and 2 pi over 3, there is no bound state in this sector up to here. Now, how could we prove this mathematically? Suppose I know that the map theta gives the infimum, the lowest eigenvalue of this operator, which is negative. Suppose I know it is strictly decreasing. This is a property I will have to prove. Then, decreasing for all theta, no, in general. Now, for all theta smaller than this angle, I write, this is just the infimum of the skeleton, this is just an identity. Then now, using the fact that it decreases, I go to this lower bound. Then I factorize the square root of t minus 0. I arrive here. Now, if I know that this operator on the numerical picture is larger than -1, then I would know that this operator is strictly is positive. They are positive, so all will be positive. Now, if I take k strictly larger than 2 minus 1/2, I will have that the skeleton is strictly positive, so no bound state. So the goal is to prove this inequality. Now, it turns out that we have been lucky, and we have been able to prove that -1 is effectively an eigenvalue of this operator with such eigenvector. If you tell me how, this is always the same. When you are doing mathematics, sometimes you just compute, and at one moment you find the solution. I don't know. I don't know how to say. If I would have to teach that to students, I don't know how to do it because. So we find it. So once you have it, of course, you replace, check it works, and then it's easy. But if you don't have it at the beginning, you don't know how to do it. Now, of course, one has to do some mathematics around this game because I have to know that this operator is effectively compact to be sure that there is only eigenvalues and nothing else. And this was not completely sure because I was dividing by something which has zeros at the bottom. But fortunately, the negative part of the operator T is such that the value of 0 also vanishes, so you have 0 over 0. You do the asymptotics, you find everything is okay, so it's perfect. So we know that there is, in the introduction I said that whether or not such type of problems, they are solvable. In my opinion, they are not solvable in general. But the hope is that many exact solutions about these T operators could be found if we work a bit. And so this would be interesting to have a catalog of such property. Then, of course, I have found one eigenvalue minus 1. But that does not tell me there is not another one which is equal to minus 2. So I compute the norm.
Just a second. How do you know that the eigenvalue minus 1 is not degenerate?
Yes, good remark. So wait a moment. So the answer is coming. Now, I compute the norm of my operator, which I know is compact. I bound it above by the Hilbert-Schmidt norm. And now this is just a bit sad because I compute the Hilbert-Schmidt norm numerically. But I am pretty sure that if I would be courageous enough, I can have a bound. Because the problem is the integral is complicated to do. So one has to bound above this integral by something which is reasonable, but which is not more than 2. Because if it would be more than 2, then you are right. But if it is strictly smaller than 1, then there cannot be another one equal to minus 1. So we know that this eigenvalue, the infimum of the operator is minus 1, and this eigenvalue is of multiplicity 1. So the theorem is like that. For all angle between pi over 2 and 2 pi over 3, this problem has no bound state below the essential spectrum. And now, if you take an angle larger, then you know that there will be at least one bound state. And how do you know that? Because if you continue above theta equal to 2 pi over 3, and since I know that this guy is strictly decreasing, so this goes down now. And I can now make this value equal to minus 1 by changing the k, because remember that this operator is divided by k minus t0. So if I increase the k, I can put this equal to minus 1, exactly. So this will prove that there is at least one bound state. Now, I have said that these operators, they are monotone with respect to the angle. It's not a trivial property. One has to prove it. So I will use the following. This is information taken from the Reed-Simon book. So an operator is called ergodic if it is positive preserving, and if for f and g both positive, you have this property, A, F, G is positive. Now, theorem, if you have a bounded operator positive, norm I is an eigenvalue of A, and is positive preserving, then the following statements are equivalent. Either A is ergodic or A is a simple eigenvalue, and the associated eigenvector is strictly positive. I know that I need to know that the eigenvalue is simple because I want to do Feynman-Hellman technique to control the derivative of the eigenvalue. And the Feynman-Hellman technique works with if you have a non-degenerate eigenvalue, or if you know that it does not change the multiplicity in the course of the variation of the theta. So the proposition is like that. For all theta in 0 pi, t theta plus is ergodic, and the supremum of theta plus is a simple eigenvalue of this operator, and an analogous statement for the odd part of the operator. And how is the proof? we know that theta plus is positive. This was proven before. Self-adjoint, this is trivial. And compact, it was proven before. So the norm, which is a soup, is an eigenvalue. Now, since the kernel is strictly positive, so for all f and g, this integral is strictly positive. So my operator is ergodic, and so I am happy, and I can continue. So now, how I continue? I take the eigenvalue E theta, like that, and I will derive with respect to theta. So you are just to believe me, you compute, you derive, and you find something which is positive, negative, because it is decreasing. So Feynman and Mann, I derive, etc., etc. But this is not at that time of the day, and
just a second. I mean, if you differentiate, you must differentiate the eigenvector with you know the eigenvector?
No, because this is Feynman and Mann theorem, and so they are normalized, and you know this is a trick that when you derive, the derivative of the eigenvectors they cancel. There are two of them, and they cancel.
But you still have to know something about the derivative of the operator and the eigenvector.
Yes, you are right. Thank you, but I wanted to skip it. We have to prove that it is analytic. This is the family is bounded analytic, and since the eigenvector is simple, and since the eigenvalue is just separate from the rest of the spectrum, you know by general analytic theory that the eigenvalue and the eigenfunction they are analytic.
So you're basically using the fact that the pointwise derivative of the kernel is negative.
Yes, because you say it like that, but this is effectively, I derive the kernel here. This is the derivative of the kernel.
So
Exactly.
So that's all you need, is that the pointwise derivative of the kernel is negative.
This is what I need, effectively. Because this is the only contribution in the calculus, because then you have the G which is here. Exactly, you're right. And the fact that, because you see, the fact that this function and this function is positive. Because otherwise I would be killed.
Not to me.
So now let's discuss about the last sector, the even sector. Now this is the skeleton we have to consider. Now you see that if I want to find a k larger than 1 over square root of 2, such that this kernel is not trivial, I need to prove that the supremum of this operator is larger than 1 over square root of 2. I think you can see it. And to prove that, one possibility is to do it variationally. So we construct a sequence of function, which is done like that. You take a function with compact support in C infinity. You take the support in -1, 1, but it's not important. It's normalized in L1. Then you rescale it so that this sequence of functions converts to the distribution delta. Then you renormalize all the things in L2. And now you know that the square of this function goes to delta. And now you compute the expectation value of this quantity, but T0, 1 over square root of 2 minus T0, has a double zero at 0. Since the function phi epsilon goes to, phi epsilon square goes to delta, so this term is of order epsilon square. Now, for the other one, we know that the phi epsilon goes to delta up to this constant. So we get this behavior. Now, we know explicitly this kernel. This is like that. This is strictly positive. So we are done. We have proven that this statement is true. So my kernel is not empty, is not trivial. So for all theta, this quantum scissor has always a bound state. in this sector even. Now you could ask, what about the other bond state, whether there are others or not? So the only thing I will offer this evening is when do we know there is exactly one bond state and not more? Because remember that we have in the odd sector we have seen that there is one bond state which appear at 2 pi over 3. Here I want to prove that in this sector there is only one bond state up to 0.77 pi. How do you do that? You split your skeleton in a regular part and a singular part. This singular part is just the kernel T that you compute, that you extract the rank 1 piece from your kernel T by taking the kernel at P0, etc., divided by this quantity. This is a rank 1 operator. Now, I would like this one to be invertible. So I do the same calculus as before. I factorize square root of k minus T0, arrive on this operator. Now, this operator, I can bound it by this one. That this has to be proven that it is monotone with respect to k. But this is trivial because you divide by 1 over square root of k minus T0. Now, this one, how do I prove this inequality? This is not mathematics. This is numerics. Because this one, this is the yellow curve. And you see that this is here, and it crosses 1 just at this value 0.77 pi. And this picture is interesting because you see that there is intertwining of crossing because there is 1 and minus 1. Next time, when the next eigenvalue for the green for this operator cross minus 1, it is just between between this one and this, etc. So this is the source of the intertwining property, which we have not fully worked out for the moment, so I don't want to state something about that. So if the angle is between these two values, I know that this operator is bounded invertible. So I can factorize it, and I get now this rank 1 operator. And 0 will be in the spectrum of this operator if and only if the norm of this rank 1 operator is equal to 1. This is trivial. The norm of this rank 1 operator can be computed like that explicitly with the function phi s given by the kernel. And now you can see that this function is decreasing with respect to k, because if you derive with respect to k, that will give you minus and the square. So it is decreasing, it's clear. So this function is decreasing. And what does that mean? That means that since it is decreasing, it can cross 1 only once, not more. So either it crosses 1 and you have one bond state, either it does not cross 1 and you have no bond state. But we know that there is a bond state because we prove it by variational approach. So we know that in this range of angle, there is exactly one bond state. The rule of the game is that I have to stop at 55, no?
No.
Or at 50? At 50?
Unless your slide pops up, say.
No, but I am ready to stop it. But I want to make a comment. So this is the beginning of a catalog of exact property about these T operators. So I will tell you that the first one is trivial because the angle pi over 2, this is the case when the two support of the delta function cross orthogonally, but this problem is fully solvable. It's separable. So you can compute everything. So you can then translate the knowledge in the Schrödinger frame into my T operators, and you get that this equation is fulfilled. Now, McGuire in '64 studied the case of n delta, attractive delta, which crossed at 0 and with a regular, with all the angle equal. This is solvable. So you can compute the exact wave function, and if you translate in this skeleton language, you get this at least for the case 3, for the case of 3 lines. For the case of n line, I was a bit lazy because McGuire does not give. One has to finish the calculation. The paper is not finished if you want. So he said that one can do it, but it is not fully done. So this is something we can do for the case with n line. And this one, in my opinion, is new. This is the one I told you a bit before. And this was done by my collaborator and myself in '06. And I have recalled what is the meaning of this operator, which are on the slide. Now, I think I should better stop, except that I would like to tell you one thing, maybe. Yeah, just this picture, and we finish on this picture. Now, suppose we will treat 3 particles on the line. And now, there is repulsion between there is 1 positive, 2 negative, and you remove the center of mass, as I said at the beginning. And now you ask what is the value of the critical charge. So Rosenthal has proven in the case of infinite mass of the positive charge that this is 0.37, that you have to compare with the real atom in R3, for which the value is something like 0.89. So you see this is a clear manifestation of enhancements of binding in 1 dimension, because you need a much smaller charge to bind 2 negative charge. Now, Rosenthal was doing the things numerically, more or less. With our machinery, we could write, for all charge, we could write an analytic function of the charge and the mass, such that the 0 of this function gives you this curve, this blue curve. And this is why, for example, I can compute the Rosenthal value up to arbitrary order, because this is exact. Now, numerically, we have, this is a variational approach. Unfortunately, we are not able to find the exact curve. This is the red curve. The exact curve gives you the critical charge. And there is one thing very, very interesting, namely that when the angle 2 pi over 3 corresponds to the case when the small mass is equal to the large mass. So you have 3 equal masses. In that case, an arbitrarily small positive charge binds 3 particles. So this is a funny problem in 1 dimension, but this is numerical proof, not a mathematical proof. For the moment, we have the mathematical proof. This is, we need the Z critical is, what is this, smaller or equal to, the Z critical, this is an upper bound. The Z critical is smaller or equal to 0.16. This is only what you can prove rigorously. So that's all. I thank you very much for your
Questions, comments, please?
It's just a comment about a little bit different physical problem where similar things arise. In, I believe in '98, studying photonic crystals with Figotin, we came up with an analog of leaky wire problem. The only difference is that the roles of parameters like energy and charge, which would be coupling constant, they play opposite roles, but it's essentially the same equation. And then we reduced it to a pseudo-differential operator on a graph, which is, I suspect, is analog of your skeleton operator. And then with Kunyansky, we've done in a couple of papers, partly rigorous analytic, partly numerical, partly analytic heuristic study of those operators. And there are some interesting features that arise exactly when you have 2 pi over 3 angles and 90 degrees angles. For instance, you can approximate pretty well those operators, but differential ones, so you get actual quantum graphs there. But we couldn't prove the result, but numerics shows that it's
It's interesting.
so there is, it's just no overlap. For instance, we were not looking for bound states. There are none there, but it's kind of ideologically
I see.
probably relevant.
Okay, thank you.
Since Pierre quoted some of our work, I should also make a comment. In this paper is Ichinoza, you mentioned we proved by something which in fact is your skeleton method, that a curve which is not a straight line but it's asymptotically straight possesses a bound state. So then, I mean, a particle case would be a broken line. So then the existence of bound state follows easily by a variational thing. And then there is a later paper with Nemcova where we treated n-half lines, of which your scissors are also a particle case.
No, I don't claim that the method is, of course, not new, in my opinion. But I just wanted to tell that it could be worse to work directly on the integral operator instead of trying to work on the Schrödinger operator. And if you did it also, okay, so we are going to form a group. And before you close the session, I would like to mention also that numerically we found this value minus 0.666666, etc. So there should be a mathematical proof. This is not normal that. So.
Thank you very much again. Thanks everyone for surviving the late session.
Inside.